Thank you very much for the introduction. And it's a great pleasure to be here today and to discuss with you what I think are great opportunities of exploring the universe with actually not just quantum, but quantum technology. Before I come to that, um, let me list my personal shopping list of what I think could be very relevant open questions still in fundamental physics. That's the list you can see here. I don't want to go too much into the details because everybody can have her own shopping list of open fundamental questions. But we all know that there is still a lot we need to understand about the universe and where we come from and so on. So like, for example, what is dark matter? What is dark energy? How do we, bring together gravity potentially with quantum information and so on? So there's a lot of interesting open fundamental questions in physics we are pursuing. And I think in the last 3 to 4 decades, mankind really has developed a very strong research program with very different means of technology, in particular, for example, collider physics, as we do at CERN, trying to understand these open questions. And today I would like to open up a new avenue of potential technology, namely quantum technology, which I believe could be very interesting to complement our portfolio of technologies that help us understand fundamental questions in physics. And that brings me to an interesting timeline, as you can see here. So quantum, and in particular, what we would call more professionally quantum mechanics, really goes back to the end to the beginning of the 20th centuries, where these gentlemen, which you can see here down, in particular Heisenberg and Schrödinger, but also aided by Einstein and several other famous physicists like Planck and so on, really started to develop a very interesting and quite novel description of what we think is relevant in nature, namely the quantum nature. And it developed into a very comprehensive theoretical framework, which as today we're describing quantum mechanics. It took several decades before the first real world application out of this new understanding of the quantum world helped us to, be implemented. And the first one really was, I think, the transistor. The transistor we're using in computers today really has an underpinning of quantum mechanics and quantum nature. Then there came the hard disks, and eventually then in the 60s, we developed laser systems, monochromatic light, which are being utilized all over different applications today. So this is what people refer to as the first quantum revolution in the past century. And I think today we have very good reason to believe that we have entered what is often being referred to the second quantum revolution. And that is mainly driven by the development in the last, 10 to 15 years in terms of trying to understand better quantum sensors. And I will come to a couple of examples of what we refer today as quantum sensors, but atomic clocks and atom interferometry are some of those examples. And these quantum sensors really in the last 2 decades have developed to a level of maturity where we are now believing they can really be utilized for real world applications. And out of it, in the next step, for example, then also unlock new potential like quantum computing and this type of thing. So this is what people refer to as the second quantum revolution. I would like to take in particular one question out of my shopping list of open fundamental questions to show you how I think we can use this new quantum technology to address this question. And that question I've chosen is, what can gravitational waves tell us about the universe and its fundamental laws? That's something which, besides dark matter and dark energy, is one of the frontier research endeavors we have been unlocking in the last 5 to 10 years. And it's a very interesting subject. And I would like to show you how quantum technology can help us to understand that better. Now, when I was talking about a century of quantum physics, then this is absolutely true. It was in the past a century of quantum physics, but there was also in parallel a development in physics, which one quite rightly could describe as another century, namely of general relativity. In parallel to the development of quantum mechanics, in particular Einstein with its special relativity and general relativity, gave us a new understanding of how to look at space-time and in particular massive objects and how this interacts with gravity. According to Einstein theory, in particular general relativity, gravity is not a force, but it is related really to the curvature of space. So it really interconnects mass and gravity with the behavior of space-time. And to put it in the words of John Wheeler, matter tells space how to curve and space tells matter how to move. And that is very much true if you really look at the fundamental description Einstein came up with. So if we have a massive object in the universe, like for example, a black hole or even two black holes, as I will show you, dancing around each other, then the curvature of space-time, because of the absolute massive objects, will have to bend and to adjust, as you can see here in this little illustration, to this mass. So it takes time for the space-time to adjust because of the speed of light being a constant, and for that reason, the information propagation that goes to space-time is basically then leading to what we would refer to today as ripples, or in a more mathematical understanding as gravitational waves. So there was the first realization when Einstein was writing down its equation that gravitational waves have to exist in order to really validate the correctness of general relativity. And I would like to show you today not only that we have discovered gravitational waves, but that these gravitational waves are really open up a completely new window in our understanding of the universe. So now let's see how gravitational waves can be generated. And that's been shown here in this little video coming from Caltech and the Virgo collaboration and LIGO and Virgo collaboration. So you have a dance of two massive objects, let's say two big black holes, a smaller one and a big one, which are in their gravitational force, and they're dancing around each other. Because of this gravitational force, as you can see in the wave description here, this gravitational waves are starting to go out in the space-time continuum. And as this dance is coming to an end, the acceleration of the frequency of these gravitational waves emitted by this dual system continues until to the point, if we are magnifying further in, when the two are really then coming to what we would call a black hole merger, when the two objects are really merging together, and you will have then the final ripple, which is being sent through the universe. Now, if we happen to have that gravitational wave now reaching Earth, what would happen to the space-time continuum of Earth? And that's been showing in a very exaggerated illustration here. So the gravitational wave is now arriving at Earth. It changes the space-time continuum, so it changes length and time. And what you saw at the end was the final ripple basically going through Earth, changing space and time on Earth. Now, what I've shown you here was a very exaggerated illustration, but effectively this is what happens on a smaller scale when a gravitational wave passes through Earth. So how can we measure gravitational waves? And there were a few very intelligent people coming up with the idea of what's referred to as laser interferometers. So we're shining laser light, as you can see here, on a beam splitter. So the laser light now takes two different paths. One path and the other path will be reflected on mirrors. The laser light comes back, it adds and meets again on the mirror. And then because of the wave nature, you can basically extract the laser light on your detection system in the end. So what happens now, as you can see here, if this gravitational wave slightly changes the length of one of those arms or even of both of those arms, you will basically imprint what we refer to as interference patterns, because laser light is nothing else than waves. So these interference patterns then will allow you to determine whether or not a length change has happened between the two different mirrors, and from this you can then infer gravitational waves. So it's a relatively clever idea. It's a bit complex, but that's the idea. That's the general fundamental principle which has been used to detect gravitation waves on Earth. Oops, next one. So now let's go back 1.3 billion years ago, when again we have two of those black holes starting their dance. And again, This is when gravitational waves are starting to be emitted now. Because of the emission of these two gravitational waves, they will come closer and closer to each other, and eventually then they will merge into one another and giving the final ripple out of that. Now, that interesting merger of a gravitational wave, which really happened 1.3 billion years ago, was our first observation of a gravitational wave being made on Earth, as a matter of fact. Oh, next one. And what have we seen? So we have built dedicated experiments from the principle I have just introduced to you, laser interferometer experiments. We have two prominent ones in the US. It's been referred to as LIGO and Livingston and Hartford. So these detection experiments eventually then saw this gravitational wave arriving. And what they then measured is what you can see here. Very short pulses, microscopic pulses being measured, which are the end of the ripple of the merger of this gravitational wave. So this is how we have detected for the first time gravitational wave of Earth. It was a verification of Einstein's general relativity, but it also gave us the opportunity to now use gravitational waves as a window. So if we now start to calculate the size of such an effect, we go back to this black hole merger, which was 1.3 billion years ago. And we know today that this was being done by two black holes, which were of similar size. And each of those black holes had roughly 30 times the mass of our sun. So for us, that's a gigantic mass. For black holes, it's actually relatively small. But with these parameters, which we could be able to extract from this, we can actually calculate how big the impact of a size effect is on Earth. And if you do that calculation, I don't want to go too much into the details, relatively straightforward in general relativity, but you basically can determine that the effect was at the level of 10 to the minus 21. Now, to give you an illustration what this means, if we take a meter as a reference, an effect at the level of 10 to the minus 1 basically means that there had to be a change to this meter at the level of 10 to the minus 21 meters. So extremely small. And it happens to be that for LIGO and Virgo, our laser interferometer experiments, which have arm lengths of kilometer size, the effect is around of 10 to the minus 19 meters. Now, that may not give you much other than that being a very small number, but let me illustrate to you what actually 10 to the minus 19 meter means. We're starting out here on that slide with 1 meter as a reference, and that's this white line here, which I'm giving you now as a reference as 1 meter. If we divide that by a factor of 10,000, then we are reaching around 100 microns, which is typically the width, the thickness of a human hair. If we again divide it further by a factor of 100, we're reaching the typical wavelength of light, which is around a micron. We keep dividing this by a factor of 10,000 now already. Then we come to the diameter, which is typical for atoms. So the size of an atom is around 10 to the minus 10 meters. If we then again divide this by yet another factor of 100,000, then we are coming to the diameter of a proton or a neutron, which are the constituents which are building the nucleus of an atom. And if we then again divide this by a factor of 10,000, then we are getting to the level of 10 to the minus 19, exactly the effect LIGO was measuring when seeing the first gravitational wave. So the length of this arm, which was several kilometers long, was changed by 10 to the minus 19 meters. So these are incredible sensitivity levels you have to achieve in order to really see gravitational waves. And quite rightly so, the three gentlemen you can see there, because they really invested a large fraction of their career, received the Nobel Prize for developing the technology and for the first observation of gravitational waves of mankind in 2016. So that was quite a big accomplishment. And these are the detection systems we're possessing today. These are the laser interferometer, which are distributed around the globe. LIGO in the US, Virgo in Italy, CO60 was a prototype in Germany, and CAGRA now in Japan. So these are the detection systems we're using today to continue observing gravitational waves after 2016's first discovery. Now, with that discovery, we have, I think, very good reason to believe that we really have opened up a completely new window to the universe, because there must be gravitational waves out there with very different frequencies and information content about what must have happened at the beginning of the universe, ranging from frequencies of 10 to the minus 19 to 10 to the minus 21 and even higher. Now, if you look at this, these are the various different effects, astrophysical effects, cosmology effects, we believe would come along with gravitational waves. And below there, you have our detection systems we're building in place of trying to measure these gravitational waves. But there's in particular one range, namely between 10 to the minus 4 hertz to around 10 to the 5, 10 to the 6 hertz, which is in particular interesting for the observation of gravitational waves, where we would think we can really learn a lot about the beginning of the universe. Now, focusing on that frequency range, and what I'm showing you here now, and it becomes a bit more technical now, is basically as a function of the frequency of a potential gravitational wave, we can measuring the sensitivity of the gravitational strain that comes along with this gravitational wave. The lines you can see here are corresponding of how such a gravitational merger of two black holes would evolve over time for different redshifts, which means for different distances with respect to Earth, typically billions of light years away. And the length is again indicating the slow rotation at the beginning towards the fast rotation and the final merger of these gravitational waves at the end. The gray area you can see here is the sensitivity region of our terrestrial experiments, in particular LIGO, which made the first observation. Now, we are working quite intensively now on an upgrade of all of these experiments, and the next ones will be roughly in the middle of 2030, 2035 being built. So there's the Einstein telescope, which is the European version. Then there's the Cosmic Explorer, which are terrestrial experiments much larger than the ones we currently have with LIGO and Virgo we are planning to build. But then also we have been planned, and it's currently under construction, to send experiments with 3 satellites to space. This is the LISA space mission, as it's called, which is the European Space Organization preparing this launch. And it will be launching in 2030, and it will really open up another paradigm of the frequency range for gravitational waves. But as we would say in London, mind the gap. There's an important gap at the moment in this, what is referred to as the mid-frequency range, in which we are not possessing any technology to measure gravitational waves at the moment. And that is a very interesting frequency range, because typical astrophysical sources like black hole mergers, but also white dwarf mergers and various combinations of it would typically be observable for days, months, and even years in that frequency range, which, as we would call it, would open up a very interesting multi-messenger physics paradigm, which at the moment we don't have. So focusing on that mid-frequency range and developing technology which enables us to measure gravitational waves in that frequency range will be quite important. Now, it happens to be that I was looking into this in 2016, and I came across a very interesting opportunity, namely to build a quantum sensor experiment, which is based on the idea of what we would call atom interferometry, which is a typical quantum sensor, namely a shaft experiment of a kilometer length. And as you can see here, such an experiment could start filling in this mid-frequency range and help us to observe gravitational waves. But ultimately, what you would like to do is to bring this technology, this quantum technology, into space and utilize really its full potential. And we have been developing a mission profile, which we have baptized EDGE. As you can see here, we'll say a bit more later, as the opportunity to bring quantum technology into space and to even further improve our capability of observing gravitational waves in this important frequency range. Now, what is atom interferometry? What is this particular quantum sensor? You might have heard about atomic clocks. These are today the most precise instruments of measuring time. This is another familiar technology of a quantum sensor, and atom interferometry is very much related to it. Now, let me introduce very quickly to you atom interferometry by using the example of light interferometry. So in light interferometry, as I showed you before, the active element is laser light, which is shown on the beam splitter. Then you are basically splitting the two different paths. You use mirrors to recombine the laser light. And because of the wave nature of light, you can see interference patterns, so-called light fringes, the same as the interference patterns you can have of waves, water waves, when you throw in stones and they overlap with each other. And from that, you can learn whether or not something differently has happened between the two different arms. Atom interferometry is conceptually very similar, but really works on the quantum level. Here, my active element is atoms. It's not only atoms, it's actually ultra cold atoms cooled down to the lowest possible temperatures. And it's not only just one atom, but rather a large ensemble of atoms we are using there. So with the help of laser light, we can construct so-called beam splitters where half of the atoms, because when I shine laser light on it, will be put to the excited state and half will stay in the ground state. And this is how I then end up to open up my two arm structures. At the end, and that is now in particular interesting in terms of the quantum nature, because we have the duality between wave and particle, an atom can also be seen in quantum mechanics as a wave. So what we can observe at the end in our detection system is not light fringes, but what we refer to as matter fringes or atom fringes. Because of the wave nature of quantum mechanics, we are capable of doing and observing this. So this is really literally using quantum mechanics as a sensing device. Now, what we have to do is not just to introduce this quantum sensor of atom interferometry to our portfolio, but really have to benefit from another quantum sensor, which again has really undergone an incredible technology development in the last 2 decades, and that's been shown here. And this is so-called atomic clocks. So we are building in my lab here at Imperial College at Blackhead. I will show you that in a second. Very precise atomic clocks, actually one of the most precise atomic clocks. And these are the devices which today for mankind are the most precise timing devices. So if we would have built an atomic clock at the beginning of our universe, which was 13.7 billion light years ago, and we would have measured its time it measures today, then we could have measured to better than half a second the evolution, the time evolution of our universe, which is incredibly accurate. And that precision we would like to harness by combining atomic clocks with the properties of atom interferometry. So really combining these two quantum sensors in one technology device, which enables us then eventually to measure gravitational waves. So that is the idea behind, and that's something we are pursuing right now. To give you an example, as we would call it in Germany, a Gedanken experiment of how we would measure gravitational waves, that's being illustrated here. I'm using atomic clocks, which is really the precursor to atom interferometry, as I said before, because it is simpler to explain, but the same thing can be done conceptually with atom interferometry. Now, let's assume we have these two atomic clocks. With our atoms, which are ultra cooled down, there's one atom species. The atoms have a ground state and the atoms have an excited state. The two clocks are now really separated far from each other in space-time. So one clock, namely the one to the left, we could refer to as our measurement clock, and the other one to the right as our reference clock, or vice versa. It doesn't matter. It's just as long as you have one reference and one measurement clock. Now what happens is we are using one laser light, namely the beam splitter, which I introduced to you earlier, to really synchronize the two clocks and elevate half of the atoms in each of the clock into the excited state, which has been shown here, half of them in the excited state, and the other half stay in the ground state. The formulation you can see here in the upper part is how we would write down the wave function mathematically. I don't want to go too much into the details, but it basically tells you that half of the atoms are now excited, the other half are in their ground state. Now I'm starting my experiment. The two clocks are now traveling through space and time. And at the end of my experiment, again, I will use one common laser beam to read out the two clocks. Now, if you look at the quantum mechanic formulation, the Schrödinger equation, technically we would call it, then you see that because of the solution of the Schrödinger equation, which is a bit complex to demonstrate, but something we're teaching to second-year students here at Imperial College and anywhere else in the world, there is a phase that's being accumulated, an imaginary phase being accumulated at the excited state. as you can see here. Now you can think of that phase as nothing else as a time measurement. So if I compare now my two different clocks, because both of them has traveled through space and time and nothing else has happened, both of them still have measured exactly the same time. So if I compare the two clocks and their time measurement, I will basically get a null result because both clocks have measured the same time. Now, what happens if my measurement clock is being exposed to a gravitational wave? In that space-time continuum, because of the gravitational wave, there will be a slight change of the length of space-time in the exposed environment for my measurement clock. Because of the speed of light being constant, that change of length will automatically translate for the clock into a change of time. And that change of time will be imprinting on the imaginary phase of my measurement clock. So if I now compare the two clocks and the time they have measured, I will realize that my measurement clock is off by delta t. That means a gravitational wave has passed through, and out of delta t, I can not only determine the frequency, but also the strain of the gravitational wave, and therefore learn where it came from, what kind of properties it had, and so on. So that's the general concept in that Gedanken experiments of how we would like to measure gravitational waves. Now, it happens to be that with exactly the same setup, there's another big fundamental open question we could explore, namely the one on whether or not dark matter exists and what its properties are. If dark matter is realized in nature, as we all believe it is, like dark energy, then it could manifest itself as very light incarnation of particles. If it's light enough, again, because of the dualism between matter and between particles and waves, we could see dark matter as a wave. And this wave now on my measurement clock will not imprint on the time axis, but it will imprint directly on the atoms I'm using to interrogate or to construct my atomic clock. And it will introduce variations which are compatible with the variations of the dark matter field which is surrounding us. And again, I will be able to measure back these variations if I compare my two clocks. Now, that variation will not have entered on the time axis, but it will have entered on the frequency axis, but it will still result in the same difference in time measured between the two clocks. So that gives us an opportunity not only to measure gravitational waves, but to also search for dark matter with these instruments, which obviously is quite interesting. Now, that's all hypothetical. So we really have to build these instruments. And for that reason, in 2018, I have been building in the UK a big collaboration. We refer to this as the ION collaboration, as you can see here. It really brings together some of the big UK powerhouses on the university side, but as well as national laboratories. So there's Liverpool University, there's the Quantum Hub in Birmingham, there's Cambridge University, there's Oxford University, there's King's College London, and we also have the National Laboratory of Particle Physics, the Rutherford Appleton Laboratory, as part in our consortium, and all of that is being led by Imperial College via me as the principal investigator. So we got more than 10 million from the UK government to build up that project and to start building up the technology one would need to use in order to measure this gravitational waves, as I just outlined to you. But also right from the beginning, we realized this cannot just be a national endeavor. We really have to, combine all the potential resources and intellects we have. And from that reason, right from the beginning, we were forming a legal partnership with a similar activity in the US, which again brings together one of the big US powerhouses, including Fermilab, the National Laboratory for Particle Physics, the Stanford Linear Accelerator Laboratory in the US, together with Stanford University, Johns Hopkins University, Northwestern University. So we're really forming a legal partnership to explore and develop this technology together. And in 2023, we were signing that legal partnership at Fermilab, where I was representing the ION collaboration. And the signature was happening, as you can see here. On the left, you see the Director General of Fermilab, so the US National Laboratory for Particle Physics. On the right, you see Mark Thompson, which is our former director of our funding agencies here in the UK. And it happened to be now the incoming director of CERN. So you can see there's quite a lot of connections to big particle physics laboratories, which this activity has already been unlocking and which I also have been fostering over some time. So this is a very important development to really start elevating the technology development from a national level into an international level. ION is really a very ambitious project, and what we have been dreaming up here in the UK is really 4 phases with a long time horizon. So stage 1, as I call it, has been funded with more than 10 million, and it's almost complete now. So we're in the final phase of stage 1, which is to start developing and prototyping the technology. Stage 2 and 3 is now then really to go to actual building of such experiments, even if they're still prototype initially. And stage 4, and that's also something I'm working very actively on because the timeline for these experiments to bring them to space is very long, is to already negotiate and talk to the European Space Agency, but also to NASA of how to best bring and develop technology so that it can go to space. And I will show you later that this is not only interesting for fundamental physics, but really also for some very interesting applications like climate change and Earth observation. This is a picture of the ION collaboration in 2021, when we had our first official collaboration meeting in Oxford. It really brings together 60 to 70 some of the brightest young minds from the UK. And another interesting aspect, which I'm very proud of, is that it really brings together 2 different communities. I'm naturally coming out of the fundamental physics community with my background being in particle physics, having worked and still living in Geneva at CERN for a long time. But we're also connected with the quantum technology community, which are the technology stakeholders. And today, in 2025, we really have brought these 2 communities together. And in particular, the younger early career researchers are the one benefiting most to be exposed to both of these worlds, which is quite a success story, I have to say. The first thing we had to do is to build 5 state-of-the-art quantum technology laboratories in the UK. 1 in Cambridge, 1 at the Quantum Hub in Birmingham, 1 in Oxford University, 1 at the National Laboratory at RAL, and last but not least, 1 at the lead laboratory at Imperial College. So that was something we did in 2022, very successfully, also utilizing novel construction techniques by using centralized production, which all has been written up and is giving you another level of acceleration for quantum technology development. At Imperial College, we got a lot out of it. So here in the South Kensington campus, we were able to build a brand new state-of-the-art 100 square meter cold atom or quantum technology laboratory, as you can see here, which really has enhanced our capabilities in the physics department of doing quantum technology development very significantly. So on the left, you see the picture when we had the handover from the refurbishment. On the right, you can see then we have filled it up with all the technology we need. And today, I have to say that the laboratory is really developing quite diverse technology development. The first stand, which you can see here in this picture, is really the one in which we are developing atom interferometry for fundamental physics, the ION experiment. But out of it, as a spin-off, if you like, in the second stand, we have building now a new optical clock, or if you like, atomic clock, which we believe will be either among the most precise, if not even the most precise clock currently being built. But last but not least, and probably as the most surprising spin-off that came out of the ION technology development, is being harnessed in this last compartment, namely that we are building there at the moment a complete novel quantum computing platform, which we think could actually be key in unlocking quantum advantage. So you see, while we have started out with developing technology for fundamental physics, there's a lot of interesting hands-on developments coming out as spin-off, which we are trying to capitalize on. So this is the team currently working at Imperial College, and complementing the teams in Oxford, Cambridge, Birmingham, Liverpool, and so on. As you can see, I had to be put into the picture because I'm traveling too much advertising the project, so I never make it into the pictures when they are being taken. But well, here you go. That's the team currently working at Imperial with me on the development of these technologies. As a side remark, and just to show you that there's really something very interesting coming out in terms of spin-off of these developments, is that we are, since few years now, planning to spin off a company, a quantum computing company, which we have baptized Precision Atomic Qubits. These are the three gentlemen who are working on spinning this out. So we're in the final stage of negotiations with Imperial College about the conditions, and we are actively talking to potential investors. The timeline is really going back to the technology development we started in 2018 on atomic clocks and the one for ion. So now in 2025, we think we are right to raise some money, and we're looking at the first raise of around 10 to 12 million to build the first prototype. And then if that is successful, spinning this company out completely and possibly making use of our industrialized campus at White City to expand the company. So there's an interesting side project that came out of ION, which I think really demonstrates the potential this technology has. So we're really in the final phase now, talking to investors and to negotiate the conditions. Now, in the last couple of minutes for my talk, I would like to highlight that obviously what I was introducing to you, in particular the UK-US partnership and national development in the UK, is not the only developments happening currently across the globe. There's many national projects currently ongoing in France, but also in particular in China, but also in Germany, which are focusing the development of atom interferometry and atomic clocks towards fundamental physics exploitation. And for that reason, because I'm coming out of a community which tries to be on an international level very inclusive, the particle physics community is very good in that, I have been also thinking of bringing together the forces on an international level and really seeing what type of synergies we can exploit. So we had the first workshop by bringing all those stakeholders together at CERN in 2023. That was followed by a workshop which we had here at Imperial College in April this year. And out of it came a very interesting development that we had so much appetite worldwide that we have been forming a legal entity which is called a protocol collaboration, the TVLBI protocol collaboration, which stands for Terrestrial Very Large Baseline Atom Interferometry for Fundamental Physics Exploitation. And as you can see here from this map, so these are quite a few interesting powerhouses of 55 institutions signing the legal agreement and now coming together to develop a roadmap of how to build this experiment across the globe. I have been elected as a chair just recently for the next 3 years, so it will be my pleasure to guide that international collaboration towards building a first incarnation of these experiments at a large scale. But going away from terrestrial applications, there's another very interesting aspect to this technology, which I think needs to be highlighted even more. And that was even before we started terrestrial investigation. We had during the COVID times, a virtual workshop at CERN, where CERN was quite supportive to help organizing it, namely for exploring the opportunities of bringing this technology into space. I don't want to go too much into the details, but out of it came a very comprehensive roadmap of potential mission proposals ESA, but also NASA could fly to develop until 2045 the technology and its use. That's been shown here. That's the roadmap we have been proposing to ESA and NASA, and we're still in very close contact with the space agencies to discuss how to best implement that roadmap from the community. And as an end product, we could have a satellite mission as the one you can see here with 2 satellites in space, which have an on-site laser beam to combine the two to measure then eventually with the ultimate sensitivity gravitational waves. But much earlier, and that's the point I would like to make, and I think that's an important one, much earlier one could benefit from that technology once it is being in space when it comes to Earth observation, and in particular in the context of climate change. I think one of the things which are a bit neglected in our discussion when it comes to climate change is actually to compile sufficient amount of data to really fully understand and model of how climate change is going to evolve. We still have huge uncertainties in these modeling, and that is because we don't have enough precision data about water height measurements, because current technology does not allow us. And that's been shown here. What you can see here is an Earth map of measuring the water heights, which is basically done by measuring the gravitational field very precisely of Earth. And you can see measuring the water height and the different color codes gives it a different thing. With classical sensors, which we have currently up in space, we are very limited to get any spatial resolution. If we were to bring a very primitive version of the atom interferometry sensors we are proposing into space, and that's shown here by the lower plot, we could have a much more accurate resolution of the gravitational wave field of Earth, hence deduce water heights, and hence collect much more relevant data that could help us to constrain and better understand climate change. And that's something we can do relatively soon and quite immediately. So I'm really trying to push agencies, funding agencies, but also space agencies into that direction to make more use of that technology in space. And that basically brings me to my final vision for 2045. I hope once we are reaching then 2045 plus, the landscape of the plot I showed you initially will look like this, with a diverse set of experiments. And there's much more interesting physics you can do with these quantum sensors, which is being listed here, which I didn't even discuss, like dark energy and several other interesting aspects. So there's, I believe, a very interesting research avenue ahead of us. And I think I just leave it here. I've taken too much time anyway, I believe. Thank you.
Well, thank you very much, Oliver. Let me invite people to put questions in. I must say my breath was taken away. I was with you all along. Dark matter I certainly would like to know more about, but I wasn't expecting ocean levels, water levels to appear. That was probably the biggest surprise for me.
Yeah.
Is the intention would be to do that from space? I wasn't clear.
Yes.
How this works. I mean, do you have to sense the surface of the water?
So back to the slide I was showing before. These are
Yeah.
so the upper slide is an actual measurement of these are electrostatic sensors which we currently have in space. So there are some space missions which are measuring the gravitational field of Earth. There are dedicated mission profiles for that. It's part of the Earth observation endeavor of both ESA and NASA. The problem with those sensors is that they have severe limitations of how accurately they can actually measure the gravitational field of Earth at a given point where they are standing. Because all is about of how well do I know the gravitational field and how accurate I can measure the gravitational field so that I can deduce what type of water height I'm actually exposed with. With quantum sensors we are proposing, you would measure the gravitational field by 4 to 5 orders of magnitude better, as you can see down there, and at each point have a much better resolution of what the water equivalent level would be. Yeah, you can, and that's relatively mathematics, but there are models out there when you measure the gravitational field of Earth at a given point in space or longitude and direction, then you can translate this into how much water height level is basically being available. And our capability of doing that at the moment from space is extremely limited. Hence, we have very limited amount of information on a global scale of how water height is changing. And with water height, obviously, is a lot connected to about climate change and all this kind of things. So this could be a big game changer of bringing that technology into space, but that means you need to make the technology space ready. You have to make sure it survives the launch and these kind of things. And that requires some investment. And we seriously have been thinking of approaching Elon Musk and SpaceX because they have a lot of expertise and also have, you know, the risk appetite for these kind of things, which at the moment ESA and NASA don't have, because for them this is still I would call it too premature technology to be considered to be put in space. And we would like to accelerate that type of development because we believe there's a lot to benefit for mankind if we can get it in space early.
Okay. Very, very interesting. I think we've got one question. Colin, is that right, Bill?
Yeah, so Colin, if you want to ask the question yourself, please unmute, or we can ask it on your behalf. No, shall we ask it? So I think so, Oliver. It's a question about separating out dark matter effects from black hole gravity wave effects in the signals, and I guess it's a kind of broader question as well. That yeah, comparing atom interferometry and laser interferometry, yeah, kind of the isolation of both, and whether that's done in the instruments themselves or via signal processing.
It's a very good question. So if you were just to have one atom interferometer experiment on Earth and you would see a signal, it would be difficult to separate its underlying nature to say this was a gravitational wave or this was, for example, an ultralight dark matter signal. But what we are really planning to do is to build a network across the globe where the experiments will have different angles. So for a gravitational wave, which usually has a direction, we would immediately see that one experiment will measure more or measure less with respect to the signal we are seeing. For example, if you have one experiment in the US, which we're currently planning, and one in Europe, they will have different angles at almost 45 degrees in which the gravitational wave can be measured. Then the same would be true for dark matter. For dark matter, it would be more isotropic. So the signal incarnation in these two different experiments would be very different. And from correlating several experiments across the globe, we would be able to distinguish gravitational waves from ultralight dark matter and measure the underlying properties very accurately. With one experiment, it will be possible, but it would be much harder. I hope I answered the question correct in the right spirit, if I understood it right.
Yeah, thanks very much. Very good.
I think you're muted.
I was just saying, from an engineering viewpoint, these are strain gauges, so you're taking very similar approaches as you would in measuring any kind of strain, I guess.
Right.
So Dave Carrington is the next, I think. Dave, if you want to come off mute and ask, or the question about how do you measure the accuracy of the atomic clocks?
You mean how do we benchmark it? So that the way how atomic clocks measure is basically not that they really measure time, but rather frequency. So we have frequency, which is 1 over time. You can basically then determine the accuracy of these clocks and what type of precision you have. But what always has to be done when you want an absolute precision, you have to measure one clock against the other one. This is when you basically then get the ultimate absolute precision. Relative precision you can do, but if you want to have the absolute precision, then you need to compare one clock with respect to the other one. And there's very different ways of how you can do it. You can use general relativity to help you. For example, these clocks are so accurate that if you have one clock on a table, which is on a meter height, and the other clock down on the ground, so you have a meter difference in your gravitational potential, because of general relativity, they will see different times. And you can exactly calculate using general relativity how big the change should be between the two clocks, and then you measure it back. So that's another way of using theory to calibrate the clocks. And they can do that. I mean, they can really measure actually not only a meter difference, but a few centimeter difference without any problems. They experience simply a different time.
Mm-hmm.
By the way, the same thing with GPS satellites. Many people don't know that. GPS satellites need to be corrected for special relativity effect because of their speed, but also for general relativity effect because we will see a different time than those satellites. So each of those satellites do have quite primitive atomic clocks, cesium clocks in there to calibrate and to measure accurately the time. Because if we would not correct them for general relativity effects, after a couple of hours, they would point to completely wrong directions here because they see a different time.
Okay, thank you for that. Asma, if you have a question, shall we ask it? So the question is, are gravitational waves from Earth constant all the time, or does it vary from spot to spot? And how does gravity help in reading the climate change?
All right, that's pretty broad. Let's start with gravitational wave. I mean, we are not really generating gravitational wave on Earth of any significant nature. We are measuring on Earth gravitational waves that have been generated billions of light years ago by massive, very massive objects, like, for example, the black hole mergers I showed you. So the gravitational waves come and travel through space-time until they reach Earth, and then they basically envelop the entire Earth, as I showed you in that video. So the gravitational wave is so far spread out that it just goes through entire Earth with a certain direction. So it's not that there is differences really, unless you are looking at angular differences, but across one longitude, for example, the impact is exactly the same. For the questions about Earth observation, that's different. This is when we use these sensors instead of measuring gravitational waves to really measure the gravitational field of Earth itself, because Earth has a gravitational field. It's not that it generates a ripple in space-time because its mass is too small to be measured, but it has its standalone gravitational field, and that's the one we're measuring at each point across Earth, and that gives us the map we are currently looking there, and that you can do extremely precisely.
Okay, thank you for that. Sanjay has a question, and it's about ambition. Oh, Sanjay,
Yeah,
do you want to go ahead?
I'm just wondering, what's the most ambitious goal your team has for detecting, observing, esoteric sort of cosmological events using this technology? Like, what would really, what is the ultimate thing you're hoping to detect with this?
Well, that's an interesting question, because I think what we would like to detect, we don't have a full understanding yet. The only thing we know is these gravitational waves, and now I'm not talking so much, and this really depends whom you're asking. I mean, you can measure gravitational waves from astrophysics. This is, for example, like black hole mergers. You learn a lot about how these black holes have been formed, how galaxies have been formed, and so on. What I am personally very much interested in are not gravitational waves that have been generated by astrophysical phenomenon like black holes, but really those who have been generated at the beginning of our universe. There must have been massive gravitational waves generated when the universe was, for example, inflating. As is one of the theories we have right now. And these gravitational waves are still there today. And they're very old, namely 30.7 billion light years old, but they carry exactly the information of what has happened at the beginning of our universe. And we want to measure these gravitational waves, be able to detect them, because once we have detected them, we can learn from them what has happened, because they still carry that information today. But we need to be sensitive enough to be able to measure those cosmological gravitational waves, which are much harder to detect than the astrophysical ones from black hole mergers. So that's
Right, so
really that's my
Right.
ultimate goal.
Oh, okay.
That's
So
very
this is actually
ambitious,
going
though.
back to the Big Bang then. You're hoping to detect
Absolutely.
the
That
vibration
is
from the Big Bang.
correct. And what has happened there, because these gravitational waves know about it. They know what kind of physics must have happened there. And that physics we would like to extract from them. So it's, in that sense, the same thing we do at CERN. At CERN, we're using a different technology. There we are accelerating fundamental particles or protons so fast and smash them with so high energies together that we're basically traveling back in time, because the condition we are creating must have been conditions that have happened at the beginning of the universe. For example, the LHC, the Large Hadron Collider at CERN, today explores what we believe is a time scale of 10 to the minus 11 seconds after the Big Bang. With gravitational waves that could even go much closer, ultimately almost to its beginning.
Wow. So,
But for that, we need to first detect them. And that is, I think, the question you had. That would be the most ambitious one, measuring cosmological gravitational waves.
Right. So is it, in many ways, it's actually going beyond even the capabilities that you could possibly imagine at CERN. It's actually taking things even further.
It could very well be going beyond CERN. Now, at CERN, the way how you would go is you upgrade the colliders, you put more energy in, and that's another project. For example, CERN is planning to even go further than where we are today. So I think the two could be very much complementary. You can learn one thing from the other and another thing from the other, because they're using different techniques. Yeah.
Right. Okay. Thank you so much. Thank you. Very interesting.
Thank you, Sanjay. We've got 3 questions and 3 minutes left, so
I'll try to be concise.
So, Henry, would you like to ask your question, please?
Thank you. Mine's probably a very quick question, but Is there any possibility that the assumption that the speed of light is constant throughout the universe, as you use in your calculations, is not correct? It varies from place to place.
It is, I mean, given the universe in which we can measure, we have no evidence of that. But we can only measure, obviously, to a certain range in light years in which we have, galaxy formations and this kind of thing. So only to that level we could really make a firm statement in saying the speed of light is constant in that vicinity around Earth. Now, if you go further, which also means going further, you're going further back in time, because the information coming to us travels by the speed of light to the best of our knowledge. It may change. I mean, many people still believe that possibly there might be no dark matter, and modifications to general relativity would explain the amount of fake dark matter we are seeing. That is not the common belief, I think, among the science community mostly, but there are still several serious scientists who think that there is the possibility. And if I've learned anything in my career, is that we need to keep an open mind. I'm an experimentalist. I would tell you, I don't think there's any evidence so far that the speed of light is violated, but I would never rule out that possibility, because we're not knowing even a small amount of the entire understanding of physics which is out there.
Okay, thanks.
Okay, thank you. A question from Vince.
Thanks. Mine's similar to the last question, but it's relating to a new experiment that's been published or about to be published on timescape, the variation of matter density in the universe not being as uniform as we've always thought. And that's affecting the way the redshift in light arriving, and it may be explaining dark energy.
Gotcha.
Do you take account? Do you need to take account of this in your measurements? And
we would not be sensitive to that effect, because what we measure is basically a gravitational wave that comes to Earth. So we're not really looking back. We measure and really observing the gravitational wave as it comes in. Where it would be relevant is then when we try to make interpretation of what that gravitational wave came from and what kind of things we would learn from it. That would be dependent to some extent to that kind of observation. It really is the question of, would the measurement be impacted? No. Would our interpretation of what it is be impacted? Yes, possibly.
thank you.
There's let's take just two questions. Do you have a couple of minutes left, Oliver?
Oh, I'm
Just to
fine,
wrap
yeah.
up?
I'm
Okay,
standing
great,
here in
thanks.
my office and I even have a coffee, so I'm okay.
Appreciate that. Thank you very much. So, Graham, if you want to come on, there's a question about directionality of gravitational waves.
Yep.
Okay, so are the gravitational waves that have been measured equally distributed from all directions, and could we ultimately point to the Big Bang?
So no, the answer is all gravitational waves we have been measuring so far since 2016 are directional, because they are basically coming from those black hole mergers or massive object mergers I showed you. That means they are somewhere located in our universe. They have a location. Now, it's hard to measure that location with the experiments we have today. That's another aspect I could have made with the mid-frequency range and atom interferometry, because we will be able to measure this type of mergers over a longer distance of time. Rather than seeing the last chirp, we would see them for weeks. We can use the rotation of Earth around the sun to trace back a very accurate location where these astrophysical gravitational waves come from. But these are astrophysical gravitational waves because they point back to the source. The ones I mentioned to an earlier question, the ones from cosmology, are harder to pinpoint because they come very likely when the universe was on its beginning at a very early stage. So they are much more isotropically distributed. So identifying a direction for them will be much harder. But yes, gravitational waves do have directions.
Okay, interesting. Final question, Alan Grant, do you want to come on, Alan?
Yes, thank you. Thank you for a very interesting talk. I just wondered, as you were speaking, whether you thought that there could be any correlation between what you've called cosmological gravitational waves from the Big Bang era to correlate with the microwave background.
Absolutely. The moment we can go back, what we would call redshift, which is nothing else going back in time, as far you can see down in the universe, that we are reaching the cosmological background when it was created, then we can start correlating these gravitational waves with the microscopic background. At the moment, the instruments we have does not allow us to look so far back in time yet, but the next generation should. For example, the space experiment I have been proposing, which admittedly will certainly not fly if on the optimistic scale before 2045 plus, that could have the ability to reach and look so far back in time that it would basically be the time frame at which the cosmological background was being generated. And hence we can correlate with it.
Thank you.
Yeah, thank you.
Okay.
David, I think it's time to wrap up.
Yes, I think it's time to wrap up, Oliver. I think I'll first say what a stimulating talk. I mean, it was absolutely magnificent. I certainly love the way you came back to our Earth and climate change at the end. I don't think any of your audience was expecting that, and that's always a good way for them to recall the whole gamut of ideas you've come up with. It certainly exceeded my expectations, the range of things you've talked about, from the beginning of our universe through to perhaps the end of the Earth in climate change. So I think I'm going to ask really for the people to unmute and to say thank you in the traditional manner. So